started. So before we write down a formal definition, let's talk a little bit about symmetry. Well, symmetry is the idea that something is the same. So many different things in art and life have symmetry. So when we look at, say, the human face or the human body, if you divide it down its median line, we are symmetric across that center line, which means down the center our eyes are evenly spaced, our ears are, and so forth. So we're going to expand that idea to talk about things mathematically. So we say a graph is symmetric with respect to and I'm going to abbreviate that as WRT, the x-axis, if when the graph contains the point x comma y, it must also contain x comma negative y. So what that means in terms of our picture is if I pick any point on the graph, so this point right here has ordered pair 4 comma negative 2, and it says if our graph contains the point x comma y, so my x is 4 and my y is negative 2, it must also contain the point x comma negative y. Well, that means I change the sign of the y-coordinate. So if I have a negative 2, I change it from a negative to a positive. That would give me its symmetric point, which would be at 4 comma 2 up here. So imagine this line of symmetry is if we were to fold our graph across the x-axis, you'll notice that the point 4 negative 2 would fold and land exactly on the point 4 comma 2. So similarly, here we would have the point 1 comma 1. Its symmetric point would be 1 and negative 1 because we changed the sign of the y-coordinate. So to find x-axis symmetry, or to have x-axis symmetry, a graph must contain the points x, y, and the point x, negative y. So that's our definition for x-axis symmetry. Well, let's grab our next one, which is also going to be, like in the previous example, of mirror symmetry. So for y-axis symmetry, we say a graph is symmetric with respect to the y-axis if when the graph contains the point x comma y, it must also contain negative x comma y. So similar to what we saw in the previous example, if I look at my point right here, it has ordered pair negative 2, 0. Because of symmetry, it must also contain the point negative x, so negative negative 2 makes it positive 2, and the y doesn't change. So this time, y-axis symmetry is imagine being able to fold the graph over the y-axis, and our symmetric points would land on top of each other. So similarly, this point right here is at 1, negative 3. Its symmetry point is going to be at negative 1, negative 3. So examples 1 and 2 are both examples of what is called a mirror line symmetry. Our next type of symmetry that we're going to have for example 3 is a different type of symmetry. So symmetry with respect to the origin is known as a rotational symmetry. So unlike the previous two, if I fold the graph over either the x-axis or the y-axis, we'll notice that it doesn't land on itself. So symmetry with respect to the origin is a rotation of 180 degrees around the origin. So if you took this graph and if I were to rotate it there we go, rotate, let's do it one more time. If I rotate this graph 180 degrees, we'll notice that this picture looks the same as the original picture. So that's what we mean by a rotation of 180 degrees. So that's our geometric interpretation. But in terms of algebra, we're going to have the following. A graph is symmetric with respect to the origin if, when the graph contains the point x comma y, it must also contain negative x, negative y. So unlike the first two, when we have symmetry with respect to the origin, if I contain the point, say here, at negative 1, negative 4, the symmetry point is I have to take the opposite of both coordinates. So negative 1 would become positive 1, and negative 4 would become positive 4. So the symmetry point would be up here at 1, comma 4. And as we noted, geometrically, that is a rotation of 180 degrees around the origin. So these three pictures are going to be the key for us to test something for symmetry, which is what we're going to be asked to do in our next example. So we want to determine the symmetries of this graph. But this time we weren't given a graph, we were given an equation. So to test for x-axis symmetry, we are going to do the following. So our first step, well, let's go look at our picture up here and see. So for a graph to have x-axis symmetry, what had to be true is if the graph contained the point xy, it also had to contain the point x negative y. So that means that for each input x, our output is going to be both positive and negative y. Or said another way, it's telling us that if we have y or negative y, the input must have been x. So to test this for x-axis symmetry, the first step is we replace y with negative y. Step 2, we're going to simplify. And then step 3, if the equation is unchanged, or if the equation is the same as the original equation, the graph has x-axis symmetry, or the equation has x-axis symmetry. So let's go ahead and do each of these. So our step 1 says we replace y with negative y. So we have x squared over 16 minus, and we replace our y with negative y. So we have negative y squared over 4 equals 1. Then step 2 says we simplify. So x squared over 16 doesn't simplify minus, but then negative y squared, so negative y times negative y is, well, a negative times a negative is a positive, and y times y is y squared, so we get y squared over 4 is equal to 1. So we simplified, and now the question is what we got in step 2 the same as what we started with? And the answer is yes. This is the same as the original. Because after we simplified, we got exactly the same equation we started with. So then our conclusion to this is it has x-axis symmetry. So as a recap then, to test for x-axis symmetry, we used the fact that we knew to have x-axis symmetry, if it contained the point xy, it also had to contain the point x negative y. So we replaced y with negative y. We simplified to see if we got back the same thing. All right, so now we want to do the same thing. We want to determine if this has y-axis symmetry. Well, if that's the case, what's the only thing that's going to change? Well, for y-axis symmetry, instead of having y and negative y, what did we have? We had x and negative x. So to test for y-axis symmetry, we're going to, 1, replace x with negative x. And then 2, we're going to simplify. And then 3, if the equation is the same as the original equation, the equation has y-axis symmetry. So once again, we're going to do pretty much the same thing. In fact, what's the only thing that's going to be different? Instead of replacing y with negative y, what are we going to do? Replace x with negative x. So that gives us negative x squared over 16 minus y squared over 4 is equal to 1. And now we simplify. So negative x times negative x is going to be positive x squared over 16 minus y squared over 4 is equal to 1. And then once again, this is the same as the original. So it has y-axis symmetry. Okay, so we've tested for x-axis symmetry, we've tested for y-axis symmetry. What's the only type of symmetry that we haven't tested for? The origin, right? So for these, we replaced x with negative x, we replaced y with negative y. For symmetry with respect to the origin, if it has xy, what does it also have to have? Negative x and negative y. So this time, instead of just replacing y with negative y or x with negative x, what do you think we're going to have to do? We're going to have to replace both, right? So the test for symmetry with respect to the origin, we're going to replace both x and y with negative x and negative y. And then everything else is exactly the same. So 2, we're going to simplify. And 3, if the equation is the same as the original equation, the equation is symmetric with respect to the origin. So this time we're going to replace both x and y with their negative. So we're going to have negative x squared over 16 minus negative y squared over 4 is equal to 1. And then we simplify. And just as we saw in the previous two examples, negative x times negative x is positive x squared over 16. Negative y times negative y is positive y squared over 4 is equal to 1. And once again, it's the same. So symmetry with respect to the origin. So it turns out that in example 4, that graph has all three symmetries. It turns out that there are graphs that have that. One of the most common examples is visualize a circle. A circle has all symmetries, right? It's symmetric with respect to x, with respect to y, and then also rotational. If you spin a circle, it still looks exactly like another circle. All right, so now it is your turn. So let's go ahead and take a look at our U try. All right, so we could go ahead and graph this, or I mean do it like we did in the previous one, but it turns out in this one that we can actually just draw a graph. So remember, our definition for graphical still holds, and since this is if the form y equals, we could just go 3x to the fourth and then minus 8x squared plus 1. And if we draw our graph here, we see our graph looks something like this. And if we look at this picture, if I fold it over the x-axis, does my graph land on itself? No. If I fold it over the y-axis, does my graph land on itself? Yes. And if I rotate it 180 degrees, do I get the same picture? And the answer is no. So this has y-axis symmetry. So we could replace our x's and our y's, and I know that's how pretty much all of us did it, because that's how I showed you in the examples. But remember, if something is already solved for y, we can just draw a graph and look visually for those symmetries. Because in our symmetries, we have this visual representation that we can use as opposed to the algebraic. So there's multiple different ways that we can think about this. And remember what I said, I am goal-oriented, not process-oriented. All right. The next thing we need to talk about is even and odd functions. So a function is even if it has y-axis symmetry. So the function that we saw in the previous example in your U-try is an even function. A function is odd if it is symmetric with respect to the origin. So when we hear even and odd function, we're just talking about symmetries again, but only two of the three symmetries, y-axis symmetry and symmetry with respect to the origin. And those are our two things for even and odd functions. So now, armed with those definitions, we're ready to analyze our graph. So for example number 5, it says, determine visually whether the function is even, odd, or neither. So even is the same as y-axis symmetry, and odd is the rotational symmetry. So when I look at this picture, if I were to fold it across the y-axis, would the graph land on itself? And of course, the answer to that question is yes. So it has y-axis symmetry, and y-axis symmetry is the same as even. So this is an even function. So if we have y-axis symmetry, that's the same as being even. If we have symmetry with respect to the origin, that's the same as being odd. All right. I'm going to do example 6, and then I'm going to have you guys do both of your U-tries together. So along that same vein, if we were to look at example 6, it says, determine whether the following function is even, odd, or neither. So we can use the same thing that we just talked about on our graphing calculator. So if I were to put this function in, I would have x to the 4th minus 5x squared, oops, I forgot to pop out of my exponent, x to the 4th, right arrow, minus 5x squared plus 5. And if I graph, when I look at this picture, I see that I have, once again, y-axis symmetry. So that would make this an even function. All right, so U-try number 5 is a little bit tricky, right? So we have to pay really close attention. So I'm going to grab a copy of that graph again. I'm going to set it down over here. And if I were to rotate this 180 degrees, my picture would look like this. And at first glance, if you're not super careful, they look almost the same, but where do we get in trouble? Well, this dot is supposed to be open, but what is it in this graph? Closed. This one's supposed to be closed, and what is it in this graph? Open. So this one is neither, even though at a first glance, if we're not paying attention to the fine details, we may think it has symmetry with respect to the origin. So that one's a little bit tricky. Okay, the next part is U-try number 6. And for this one, we're going to want to just draw a picture with our graphing device. So if we were to graph g of x on our calculator, we would have 2x cubed minus 6x, and we graph this thing. And when we look at that picture, what type of symmetry does it have? Well, if I go ahead and do this, and I flip it over, we'll notice that these two do look the same. So that's symmetry, that's rotational symmetry. Which means it's going to be odd. All right? So with these ones, it's kind of nice. We can for ones where they're functions, we can just graph them on our graphing device and look for y-axis symmetry or rotational symmetry. And if it helps, literally just turn your calculator 180 degrees and see what it looks like, right? So you can do these to help you visualize what's happening. All right.